Hi, my name is Anjani Rana and this is my oscillation lab. To introduce the lab, we'll be creating a computational model consisting of an object attached to a spring and rope, and we will be comparing this model to observational data gathered using Tracker from a video provided by Dr. Schatz. There are two important physics principles that are covered in this lab, the momentum principle and the energy principle. First, we'll talk about the momentum principle. This principle is used as an initial step to determine the amount of force acting on the object, and using this information to find the velocity and position of the object in iterated steps. The net force is calculated by adding together the spring force and the force of gravity. Now we'll take a look at our while loop and see how the momentum principle was applied to our code. Here we calculated the force of gravity using the equation F_grav equals negative mass times gravity constant times j hat. Then we calculate the spring force using the equation F spring equals spring constant times distance s times L hat. We then add together these forces to calculate F net. We use F net to calculate final velocity by using the equation final velocity equals initial velocity plus F net over mass times delta t. Finally, we update the position using the final velocity found using the equation final position equals initial position plus final velocity times delta t. We use final velocity because the force is non-constant. The second principle that is explored in this lab is the energy principle. The energy principle states that if no work is being done on a system, the change in energy is equal to zero. There are two types of energy which combine to equal the total energy of the system, and these are kinetic energy and potential energy. There are two sources of potential energy in the system, gravitational potential energy and spring potential energy. We can now see how the energy principle was applied to our code in our while loop. First, we calculated the potential energy using the velocity found earlier from the momentum principle, using the formula 1/2 times mass times velocity squared. We find delta K by subtracting the initial kinetic energy from the final kinetic energy. We then calculate the gravitational potential energy using the formula UG equals mass times the gravity constant times the height of the object. We subtract the initial gravitational potential energy from the final gravitational potential energy to find delta UG. Finally, we calculate the spring potential energy by using the equation 1/2 times the spring constant times s squared. And we find delta US by subtracting initial US from final US. Because no work is being done on the system, delta E is equal to 0. Here we can see our energy graph showing the change in the different types of energies versus change in time. The magenta line indicates spring potential energy. The red line indicates gravitational potential energy. The cyan line indicates total potential energy. The blue line indicates kinetic energy. And the yellow-orange line indicates the total energy of the system. Gravitational potential energy and spring potential energy add up to equal total potential energy. And as we can see, total potential energy and kinetic energy oscillate with equal amplitudes but in opposite directions. As a result, the total energy of the system is equal to 0. Here we can see the differences between our observed data and our predicted data. These two graphs do not match up, and this is due to the fact that our predicted data does not account for air resistance or drag force. We will now look at our GlowScript code that resulted in these two graphs shown. We'll select a file, and here we can see our predicted model oscillate as our observed model also oscillates. To answer our first question of if the energy principle is justified, we can see here that there's no change in the total energy of the system, as indicated by the yellow-orangish line here. The total potential energy and kinetic energy oscillate in alternating patterns with equal amplitudes, and when these two are added together, the total change in energy is equal to 0. Because no work is being done on the system, there is no change in energy. For the second question, we estimate the oscillation period from our x and y data, and we determine that for the x data, the oscillation period is 1.614 seconds, and for the y data, the oscillation period is 1.424 seconds. The difference in oscillation periods is 0.19 seconds. This difference could be due to the fact that the forces acting on the object in the x direction are due to the mass of the object and the spring constant, whereas the forces acting on the object in the y direction include the force of gravity. This concludes my presentation. Thank you.